All right. Overview, everyone. Sorry, I'm late a little bit. Today was one of those days that I'm having 100 things together. Um, okay. Um, let's continue talking about coherency protocol. If you remember, let me just very quickly go up. So the coherency protocol the coherency problem was this problem where we had local copies, private copies of data in our private caches in a multi-core system. And since they don't announce and update other cores, we might end up with different copies of the same data in different caches. And that would result obviously into correctness issues. And if you remember, we told you that we cannot fix this problem, like we cannot eliminate this problem because we want to share memory addresses. So we want to share this, for example, Z here. And we want to also have private caches because without private cache, we're going to have terrible performance in terms of average access time. On the other hand, we also want to have shared cache because shared cache gives us better utilization and easier to share and all those things. So we're kind of in this situation where we want to share, we also want to have private cores. That's why the problem of uh, uh, coherency is an inevitable problem. It's an unavoidable problem. How do we solve it? We introduced the notion of snooping. And essentially, we said that the idea is that whoever updates any copy of data, whether in local or global, they have to announce it to everyone else. And everyone else has to pick this up and basically use it to update their own records. We start with like this coherence states, and we said that like the bare minimum that you need to have is 2 states, modified and invalid. Invalid means that I don't have the copy. Modified means that I have the copy and nobody else has it. And modified also is used when you're modifying the data. But we quickly saw that modified alone seems to be a little bit inefficient because there might be scenarios where multiple cores wants to read some data. They don't want to modify, they just want to read it. But the act of reading one will cause the other core to be invalidated, even though that they're just reading, so they don't changing. So that's where we introduce the idea of a shared state, where the cache now can have 3 states: the M, which is the modified, the I, which was the invalid, and now a new one called share, which we call S. The difference between S and M is that if someone wants to read, they go to the shared. If other people also wants to read, they also go to the shared. So a particular line could be in multiple caches at the same time. If anyone tries to write and update that value, then it will issue a write. Everybody else will invalidate, and then that core will go to the M state, to the modified state. And again, if someone else wants to read it after the core has written through, the core has to write it back to the memory, and then goes to the S states, and the other core will also go to the S state. This is what we call the MSI cache protocol. And it will look something like this as we show. So you kind of think about it as a state machine, 3 states: the M state, S state, and I state. There are conditions from switching from one state to another state, depending on the activity of the other. Keep in mind that we also have the write back, which is whenever you switch, you also have to write back from the memory. Everybody in MSI gets their values from the memory. It's not a cache to cache transfer. Everything is memory to cache transfer. Okay. Um, And one last thing to say is we usually use write-back strategy. In most cases, that's why we have the dirty bits, and that's why we write back. If you had write-through strategy, then write-back is not necessary. Whenever whoever wants to write it to the cache and memory at the same time. So when we want to, for example, switch from M to S, we just switch from M to S without needing to write back because this is write-through strategy. If you don't remember what the difference between write back and write through, the idea was write back is whenever the core wants to update the value of the memory, it updates the cache, but don't update the memory. We will have an extra bit called dirty bit, which becomes 1 if the value is modified. It's dirty. Otherwise, it's 0. Whenever we evict it from the cache, then we will check this bit. If this bit is equal to 0, then we write it back. Otherwise, we just discard it. Okay? Write-through strategy was whenever the CPU wants to update the cache, it will also update the memory. So any write from the CPU will do two things. It will update the cache, it will update the memory at the same time. So this will issue more writes to the memory, so it takes more bandwidth, creates more traffic. But it makes the eviction of the cache lines and all much simpler because you don't need to check the dirty bit. You don't need to maintain the dirty bits and so on and so forth. So this is kind of the trade-off. Then we start talking about optimizing MSI, and I told you that there's going to be 3 states. Very last thing that we said last time was the E states, the exclusive state. The reason for having an exclusive state was if one cache is in the S state, but it's the only cache has the valid copy of the data, if they want to modify it, they can switch from the S state to an M state without announcing it to anyone else because there's no other cores that has this data, so there's no point of announcing it. In MSI, we cannot do that because we don't know whether we are the only one or not, right? Because shared doesn't tell you that whether you're the only copy or there are multiple copies. But if you have another state called E, then we can distinguish between E and S. So E and S are the same thing. They both have copies of clean data. E is exclusive, which means that there's only, out of all the cores that we have, only one core has this data. S is, there are at least 2 cores that has this data. The benefit of having S is that when you are in S and you want to write, you don't announce it. You do silently switch to M. In other words, you don't broadcast anything to the snooping network. Nobody sees and knows. So in other words, from the other core's perspective, you might be either in E or M, but that doesn't matter. Why this is beneficial? Because it reduces the amount of broadcasting. And reducing broadcasting is helpful because it reduces the traffic and saves energy, saves time. And then there are many instances that one core and one core only has the data. As I said before, there are many instances that core X, for example, has some program that is not shared with other cores. So there's no sharing going on between the core and the other cores. In that case, essentially any read and write will go to basically I, E, and M, really, because there's no sharing between them. So that's actually very, very nice and helpful in most cases, because if you're the only one who has access to this data, why do you broadcast it to someone else, right? So that's why E is actually quite popular, and it's a very important state in your cache, okay? So now that we kind of so this is, by the way, called MESI. And then you can actually, we can definitely, I think the TAs will have also examples of all these different cache states in the discussion session. So we're going to further optimize this by introducing 2 more states, O state and an FS state, okay? Is there any questions so far? Yeah. Mm-hmm. Mm-hmm. So the question is about exclusivity. Means that, so for example, let's say we have 4 cores, okay? each one has their private cache. This is L1 private cache, okay? L1, L1, L1. These are private, okay? Which means that this core cannot access the data here. These are private cache, okay? So for example, let's say we want to read an address. Let's say address equal to 100 or whatever. That will translate into some physical address. That means that we're going to store something here in this cache, okay? So if this address 100 is the only stores in this cache and not in the other caches, we call that this is exclusive to this cache. Why we might have this value also stored here? Because imagine that this is a parallel program that everybody is, like, imagine the partial sum examples that I gave you. Like, if this is partial sum, then others probably going to have a copy of that in their caches as well, right? So that's the difference. All right, so let's talk about why we need these two other states. So the first example that I'm going to give you is this. Imagine the scenario like this, that there is a core in M, okay? And of course, when one core is in M, others has to be in I. There's no possibility that one is in M and the others is like one of them is in S. So one is in M and the others are all in I. Now a new core wants to read that data, the same address. What should we do? We told you that M will write back their data to memory. The other core, so basically the process will be this. M will write back. Then it will go to, M goes to S. And then, so this is, let's say, core number 1. And then core number 2 will read the data from memory. And then from I, it switches to S, right? So read it and go to S, okay? And so after this process, both of them will be in S, and the dirty bit will be equal to 0. There will be a write back issued, okay? So that's great. But then the question is that looking at this, seems that, core number 1 has the data, and core number 2 wants to read basically this data has been written back to the memory, right? So it seems that there is an unnecessary write to the memory and read from the memory in this process, which could have been just easily fixed by forwarding the value from the one cache to the other cache, okay? Why this would be helpful? Because reading from memory is slow, but cache-to-cache transfer could potentially be very fast. And also, reading from memory creates new traffic versus cache-to-cache transfer could be much faster and much easier and simpler to do, okay? So if we can somehow figure out how we can do this, this cache-to-cache transfer, then we can improve our system, right? So how do we do that? So essentially, we introduce this new state called O, which stands for owner. And what it does is basically when the one cache is in M state and the other cache is in I state, when the read is issued, the M state will provide the data to the other cache, so no write is necessary. But then instead of transitioning from M to S, because remember, when you're going to S, you're saying that my data is clean. So it's already written back. So I cannot, if I don't issue a write to the memory, I cannot transit to S. So instead what I do is that I transit from M to O. So O is still maintain a dirty copy, but it can be shared with other caches. So if other cache wants to read it, I'm the owner, I provide the data. So, but still I have the dirty copy. So whoever goes to the memory and tries to read it is going to read an incorrect value. You have to go to the owner and ask it for the owner, okay? How do we do this? Essentially, again, so this is a broadcasting mechanism. So let's say core 1 is owner, and core 2 wants to read it, okay? So core 2 will broadcast that address on the bus. Core 1 will see it, and it's basically going to intervene into this process. Instead of this core going to the memory, C1 going to provide the data, and then C2 going to read that data. Okay? There are a bunch of questions. Yeah. The question is, when do we transition from O to S? We don't transition from O to S, but we can transit from O to either M or I. So when do we transit to I is when there is another core wants to write. When another core wants to write, you no longer become the owner. The other core becomes the owner. So you have to transition from O to I, but you have to also write back at this moment because now you have the dirty data. And then the other core will transition from either S to M or I to M, whichever they are. And then again, as this process continues, that core becomes M to O, and then O to I, and O to M, and so on and so forth. Okay? Yeah. Mm-hmm. Mm-hmm. Yeah, good question. So if you are the owner of data, and essentially whenever any of these either M or O, for any reason that are decided to be evicted, they will be written back to the memory, okay? Because they have the dirty bit. And then there will be another core. Let's say, for example, there's also other cores in S. Uh, so they already have the data. If there is, let's say, another core that is in I and then wants to switch to S, but there is no owner, what will happen is that they have to still go to the memory and bring it. So nothing bad happens. So essentially, as I said, C2 will announce that I want this data. Either there is an owner that provides that data. If there is no owner, it will just go to the memory and break it. Yeah, I had a question, yeah. Exactly. So the question is, when we are transitioning from M to O, there is no write back. Yes, that's exactly what it does. So there are two good things that are happening here, right? No write back from M to O, and then cache to cache transfer from M to another core which is in I. So two things that kind of improve the performance. Did you have a question, or did you answer the question? Okay. Any other questions? So with O, we can have then MOSI, okay? So like again, so if we look at the MSI and then we have MOSI, so essentially I'm adding O to MSI. So if I have MOSI, essentially what I have is everything is similar to MSI. The only difference is that if you're in M and a new core wants to read it, you go to O and provide the data. No need to write back, no need to from memory read. If you're in O or M and other core wants to write or for any reason needs to be evicted, then you write back and invalidate. Okay? That's the idea. Yes. Question is, if you are in M and then the other core is in I, if it wants to read, what happens? So this one goes to O and this one goes to S because it has the clean. From their perspective, they have the clean. There's only one core that can go to O. You cannot have multiple O's. Yes. So the question is, what about E state? Yes, you can actually have MOESI. Uh, and then this is also very common. But these does not, so they're not dependent to each other. You can have an E state and or an O state, or you can have both, or you can have neither. Typically, you don't go, as I said, like the baseline is having at least MSI. You can technically have MI, but nobody uses MI, so usually MSI is kind of like the bare minimum. But then you can add O or E or both. Okay? So last one. I'm gonna do the example later, but and as I said, so this is just actually answering your question. You can have E and O at the same time. As I said, they are doing different things, so there you can benefit from both. But of course, the trade-off is your coherency becomes more complicated. You need to maintain more states, but you can benefit from them. Last one. So let's say there are multiple cores in S. Okay, one or multiple core in S. And someone wants to read the data, someone else, like a new core. So let's say core number 1 and core number 2 are in S. And now core number 3 wants to read this data. Who should provide this data? There are a bunch of ideas, right? So the first one, the easiest one, is that it reads it from the memory. The second idea is these two kind of like do round robin or some form of like a random. So whoever wins, they provide the data. But the cleaner option, the more straightforward option is when we have what we call a forwarder, which is responsible for providing clean data. So forwarder is very similar to O. So owner. The difference between the forwarder and owner is that owner has the dirty copy, the forwarder has the clean copy. But both of them provides this cache-to-cache transfer. Okay, so whoever wants to read it, they provide it. So this is what we call an F. Uh, um, so essentially, how do we do the forwarding? Forwarding usually is coupled with E, the exclusiveness, because for forwarding, you need to know the notion of being the only one. So the way it works is that you start from I, you go to M or E, the first core that has that data. It has to be exclusive. Then if you're in E and someone wants to read, so there's another core that wants to read, instead of going, remember I told you that in the past you will go to S, and this one also goes to S. And in this case, this one has to read from memory. So with F, what will happen is that you have I, you go to E, and then this is I. This one wants to read. This one still goes to S, but this one will provide the data and goes to F. Okay? So at the end of this process, one core is in F, the other core is in S. Now, if there are more cores wants to read, so let's say another core, so this one goes to S, and it will be the data will be provided by the other core. So that core stays in forwarder. So as long as there are only reads, one stays in forwarder, the other guy stays in S. What will happen if someone wants to write? Whoever wants to write will invalidate the rest. So for example, if this guy wants to write, this will go to M, this will go to I, and this will also go to I. Okay? And then the process continues. So if someone wants to read, then again, if there is O, this one goes to O, and this one goes to S, and this one goes to S, and so on and so forth. Okay? Questions? So this is what we call MOESIF. This is all together, okay? So this will be basically the process if I have all of them. From invalidate, if I'm the only cache that has the data, I go to E. From E, if someone wants to read, I go to F, okay? If I want to write myself, I go to M, but I go silently, so I don't need to broadcast, so that's the difference. And then if I'm in the I and wants to write, I go directly to M. But then if someone else wants to read, I go to O, right? And all of these, I'm not showing, but all of these guys can also go to I, right? So at any point, you can go to I. If someone else trying to write, or for any reason, you need to be evicted. So going to I is always an option, which I'm not showing here. Okay? And then you can also have I to S if you are not exclusive, right? So if you are in I and you want to read, you go from I to S if you're not exclusive, right? It means that there's already a core that are either in O or in E. Then you just go to S, okay? And this is called MOESI. As I said, we typically don't have like MSIF because we need E for F. So at least we have MESIF. We do forwarding with E. Otherwise, it doesn't make much sense. Okay. So let's actually like go an example with all of these guys together. Let's say originally everyone is in I, okay? So this is for one address. Remember, for every set in your, like every block in your cache, you're gonna have coherent state. So when I, for example, show you core number 1, core number 2, core number 3, there are thousands of these I's and S's and F's and so on. These are per block. I'm just showing you one block. So I'm assuming that all these writes are to the same address, but just keep in mind that there could be multiple, all right? So let's, for example, let's start with some sequence. Let's, for example, sequence number 1. Let's say, for example, core number 1 gonna read. So the notation I'm gonna do is either I do R or W, and then the number after that is for the core. So if it's R1, can you tell me what should happen with these cores? So for core number 1, what should we do? Which state should we transition to? Yeah, so we can go to E because everyone else is in I, so we can go to E. What about core 2 and 3? I, right? So you have nothing to do with this, you stay in I, okay? So if there is another R1, what happens? Yeah, it's still the same, so you still stay in I, so just keep that in mind. So you basically repeat this. Well, then let's say, for example, let's now from here, let's consider two options. Let's say, for example, core number 2 wants to read. What happens here? Someone? Yeah. Mm-hmm. Sure. Then what about 3? Okay, there you go. And then let's do, for example, a different color. Let's say, and then of course R3 is the same as R2. There's nothing to do here. And then let's say, for example, we will have write 1. What should we do now? So from here, if we have write 1, what do we do? Yeah. MII. The only thing is that from E to M, this is silent, so you don't broadcast this, right? And then let's say, for example, we have, let's go with another example. Let's say we have W2, then what should we do? Have W2, what should we do? IMI. Is anyone wondering why IMI? Do I need to write back and do this, or can I just do from E, do I need to write back? No, so no write back is needed, right? Make sense? Okay, so let's, for example, from this continue. So let's say we are in IMI. Let's say, for example, R3 wants to read. Then what should we do? Anyone? So we go IOS, right? And then do we issue a write back? Yeah, so we don't. From M to O, you don't issue a write back. And then we also don't read it from memory. So basically, this is what we call a cache-to-cache transfer. So it's done by this, right? So it's provided by the cache, okay? Let's say, for example, R1 wants to read. What should we do? Want to go for it? Uh-huh. So we are in iOS, and R1 wants to read. Anyone else wants to chime in? Yeah. Yes. So we go SOS, right? And who provides the data? Core 2, right? So core 2 provides the data, and we move forward. And then let's say, for example, What if we have W3 at this point? SOS W3. What should we do? Yeah. And then do we issue a write back here? Yeah, so we issue a write back. We usually show it with some, I don't know, like in this class, we show a star. You can do whatever you want. Make sense? And then there are various different options, right? So there are three, like, there are multiple different possibilities here. Does that make sense to everyone? Yeah. Oh, so you're asking, since this one is writing, why do we write back here? Is that your question? It's instead of write 3, write 2. Oh, okay. Good question. So if it's instead of write 2, write 3, let's see what happens. So let's say we are in SOS, and then we have write 2. Someone wants to say what happens? Yeah. We fall back to M, and then what happens to this guys? Yes, I. And then do we write back or not? That's your question. Typically, we do write back because it's usually easier to maintain a dirty copy that way and not kind of split it into multiple solutions. There's also for consistency issues, we do write back, but it's possible that technically you don't need to if you because it's actually write after write, right? So the newer write is really the value that you need to care about. So you can also, optimize the writes if you want to. But typically, at least in this class, we assume that you write back. Yeah. Question is, what is the relative speed between getting it from L1 directly versus forwarding? I think typically like forwarding is within like consider level 2, level 3 hits kind of thing. But it's also depending on the implementation. They try to have the cache to cache transfer almost as fast as the same cache. Yeah. So you will consider it as like L3 kind of latency kind of thing. Any other questions? So hopefully you're gonna have fun with this, with different kind of possibilities. This is actually going to be your CA3. So in CA3, we're gonna give you 4 cores and MOESIF, and we're gonna ask you to basically do this for us and updates the stats showing us like how many like write back you've had and how many invalidations you had and all those things. Okay? I'm gonna post it hopefully tonight, so the details will be there. All right, so to kind of summarize why we add things to our MSI is there are 3 things kind of like we try to do, right? So we try to remove unnecessary broadcasts, and E, for example, was an example of that. We try to remove extra write-backs from the memory through the cache-to-cache transfers and through the O states. And of course, we introduced the forwarding and cache-to-cache transfers to make the read data faster. Okay? Um, any final questions about MOESIF? Great. So there are a couple of things I want to quickly share, and then we're going to move on from cache coherency. The first thing is called fault sharing. Okay. So I told you that we can assume that these coherency states are at the block level. Okay. But then if we have this, for example, if we have a set associative cache that has multiple blocks, multiple ways, then if we only maintain one coherency state per set, it means that now for multiple blocks, we only have one coherency state, okay? And there will be scenarios that, for example, one of the blocks are shared, but the rest are not shared. And if we, for example, want to invalidate, not only we invalidate that block, we'll invalidate the entire set. Okay? This is usually what's called false sharing, which means that you're not sharing, but the block is being penalized because the other blocks on that line in that set is being shared. Okay? Why do we do that? Because of simplicity, right? So because multiple, having a coherency state per block might be very expensive. It also requires lots of reads and writes and all that. Versus at more bigger, like set level or multiple set level, it's much more cheaper. So that's the reason that we do. And then false sharing, of course, gonna create more misses, because if you didn't have coherencies, this wouldn't have been invalidated, but because of the coherency now you have some lines being invalidated. And this is usually what we call a coherence miss. So remember that we had compulsory, conflict, and capacity miss. So there is the fourth miss called coherence miss. So these are misses that, because we are sharing the coherency states among the blocks, we are falsely invalidate some lines that we shouldn't have. As a result, we're going to have misses that we shouldn't have. Okay? This is different than misses that you have. So if, for example, a line has to be invalidated, that's not a coherency miss. But if it's a false sharing and then you're invalidating more blocks than you're supposed to, that's called coherency miss. Okay? So for example, like, if you have 200 and 201 and 202 all within the same set, and then let's say 200 is shared, but 202 is not shared, but when you're invalidating, you're evicting both of them at the same time, and the next time you're reading 202, you're going to have a miss. This is what we call a coherency miss. Okay? So this is different than compulsory and conflict and capacity. The another thing is that, is snooping is the only and the best option? The answer is no. And the reason that snooping may not be the best option in some cases is the scalability. So for example, I gave you 4 cores and show you that with 4 cores, every core needs to broadcast and other cores needs to listen. So now think about 64 cores or 128 cores, right? There will be tons of these broadcasts and this checking, because for every single core, all the other cores needs to now follow along and broadcast. So this is going to obviously lead into scalability issues when we have many, many cores. So what can we do instead? Another possibility is what we call directory-based coherence protocol, which essentially we have a directory for each cache line where we kind of maintain who has what, okay? So what we do is that at the memory level, so think about every memory address has this bit that, let's say I have 8 cores. I'm going to have zeros and ones in this, and this zeros and ones, consider them as presence bits. So basically, if it's 1, it means that it exists in that core. If it's 0, it doesn't exist in that core. Then if I want to kind of update things, I no longer need to broadcast. All I need to do is basically update the directory. If everyone access to the directory altogether, all I need to do is updating and changing the directory. And then this way I completely get rid of the broadcasting. The downside of this is that directory needs to be stored usually in the memory. There's no other place that I can store the directory. So essentially every access needs to go to the memory and come back. It's a little bit slow, and also it requires more space in terms of the space that it requires in the memory. But no broadcasting is necessary, no snooping is necessary. Communication is only to the memory and back. There's no need for communication between them, and so on and so forth. You can still have all the forwarding and all the tricks that you want to have if you want to, but it has to go through the directory and come back. Yeah. So the question is that if the directory is in the memory, is it faster to just use using directly the cache? Remember, this is kind of like off the critical path. So it means that, for example, you read it from your cache, but then instead of broadcasting it to the bus, you go to the directory and update the directory. Or for example, if you issue a write, you go to the memory and do that. So for interaction with CPU, you still use the cache. For updating and snooping, you do this way. And also keep in mind that we're talking about massive systems. So when it's like 64 or 128, if like the snooping, the bus overwhelms with this request, then your snooping also going to be very, very slow anyway. So you might actually as well go to this. There's few details about broad directory base that I'm not going to go through. So just keep in mind that this also exists, but you don't need to know a lot about directory base. So we're not going to ask you questions about like maintaining directory-based cache coherent. If you're interested and you want to know the details of directory base, feel free to search and learn. But just keep in mind that this is another option. Our main focus is snooping, which is also being implemented in quite a lot of modern systems. Okay? So that's it with the cache coherency. As I said, this is going to be used for your computer assignment 3 as well. So hopefully you'll watch this lecture and previous lectures to kind of learn. Any final questions about coherency? All right, so let's have like a 5-minute break, and then we can start talking about consistency. Okay. Um, so let's talk about memory consistency. Remember I told you that when we move to multi-core systems, there are two problems we need to solve. The first problem is the memory coherency problem. The second problem is the consistency problem. To remind you, what was the consistency problem? Imagine a scenario like this, where we have two cores, and they're trying to write and read from two addresses, Z and W. Z and Y. And they're also writing things to those addresses. The problem that we're going to have is the value of x1 and x2 will be dependent on the orderings of these instructions, okay? As we're going to talk about, and probably some of you who are familiar with parallel programming already know this, that there are two class of problems that cause this issue, that x1 and x2 essentially can get various values, can get 0 or 100. The other one can also get 0 or 200. And another big problem that you're going to see in consistency is that if you run this multiple times, each time you might get a different value. So it's not something that you say that, okay, this is the code I've written, and it always gets, let's say, 0 and 100, and not 0 and 0 and 0 or something like that. As I said, there are two main problems in memory consistency. Let me see if I have it. No, I don't have it here. So there are two problems in memory consistency. One is you just wrote a bad code. When I say bad code, it means that a code that has what we call race condition, which means that you just didn't really write it in a way that follow the program order in both cores. There are ways that you can remove the race condition or use other tools to fix that, and that's one thing that we're going to talk about. The second thing is more on the hardware side and the reasons that we reorder things. Remember I told you that we have out-of-order execution, and in out-of-order execution we can reorder reads and writes. And then remember I told you that, for example, you can LS queues, load store queues, and in load store queues, we might be able to also reorder things if you want to, and so on and so forth. So what will happen is that a collection of software and hardware will cause consistency problems. which means that when we say problem, the reason for being this a problem is the output of your program differs, but you want to be deterministic behavior of your program. So you want to fix this issue somehow. So as I said, there are three reasons that you might have this. Uh, as I said, there could be reasons such as raw data hazards that could prevent this from happening or cause this. There's correctness issues of different orderings, and then there's might be load store queues that cause this issue. For example, imagine that the compiler, since these two, for example, let's say these two instructions, since these are independent from each other, imagine that the compiler decides to reorder these instructions. Because remember, when we had raw data hazard fixed the issue of same addresses. So for example, if this was Z, then this falls into the category of a raw data hazard because there is like write after read or read after write. I cannot, for example, move this before this, because if I did, then I'm going to get a wrong value into x1. So we already fixed that in our out of order execution. But here, what I'm showing you is y and z are two independent addresses. So there's perfectly fine that they can be reordered per core. Nothing bad happens if this is the only program that is running on the system, one core. The problem, though, is that if the compiler decides to reorder things, that might impact the other core. And again, as I said, the ordering might be different. So that's what we call the memory consistency problem, and that's why we have it. It's not a raw data hazard, but it could cause consistency, correctness issues, and it could be either caused by load store queues, or by the compiler, or by collection of both, or just by the bad way that, bad code that you write in software. There is another thing that you have to be, so as I said, there are two reasons for this. One is store and loads within one core might be reordered because they are different addresses. So they're not dependent to each other. The load store queue and or the compiler might decide to reorder these things, and that will cause a problem. The second problem is, as I said, is race conditions, is that the timing between the cores might be off. And as a result, these things might interleave to each other. And even without reordering, so assuming that you don't reorder anything, you still might have issues, okay? So these are the two reasons that you have the consistency problem. Another thing to keep in mind is that you might ask that, oh, wouldn't this be the same coherency problem, or why coherency problems and coherency states and all cannot fix this issue? The answer to that is that coherency was for the same addresses, okay? We maintain coherency of multiple different copies of the same address. So like the S and I and M and O and all those things were all for the same address, okay? Consistency is for different addresses, okay? So consistency means that reordering things in one core of different addresses will result in values and different outputs of the other core. So this is like very different than the coherency problem. So just keep that in mind, that these are two separate problems. One is about making sure that the copies that everybody has from the same address is the same and coherent. The other one is about the ordering of these and making sure that the orderings maintain similar. So how do we fix this consistency problem? Remember, there are two reasons for this. One is race conditions in the software that you wrote. And the second is that the hardware might also decide to reorder things on top of the bad code that you write. So that makes things very convoluted. So how do we fix this? The first fix that you should do, and everybody does, is that, of course, you have to make sure that the synchronization problem, the timing problem between the cores, not the reordering problem. The timing problem between the core is the programmer's job to fix it. Okay, hardware is not able to fix this problem. So if your program for any reason has a race condition, this is the programmer's job to fix this race condition. Okay, so for example, if hardware says that I'm going to always run this instruction first and then this instruction for second in core 1. And then for core 2, I'm going to do the same. I'm going to run this first and then run this. I'm not going to reorder anything. Even if this is load and stores for different addresses, I'm going to promise you that I'm not going to reorder. Okay? That's the best thing you can get from hardware. But if, for example, your execution is like, let's say let's call this A, B, C, and D. If the execution is A, B, C, D versus A, C, D, B versus A, C, B, D, and so on and so forth. These are all possible sequence of instruction in this case. Remember that we still maintain the A to B and C to D kind of time, but they can interleave with each other because these are parallel, right? And then their timings might be off. So might be first core running and then second core, might be exactly at the same time with a little bit interleave and so on and so forth. So you have to write, as a programmer, you have to write a code such that any of these possibilities will produce the same result. This is what we call a race-free or timing-free programming, okay? And that's why usually writing parallel programming is very, very hard, because you have to envision and anticipate these problems and write your program in such a way that it doesn't have these solutions. Good news is we will introduce some hardware primitives that will help you to ensure a particular sequence. So for example, let's say that you write a code that has to work this way. So you want to somehow ensure that A and B happens first, and then C and D. So you want to have some order between the cores. There are primitives that you can use to do this. You're probably familiar with barriers and semaphores and locks and mutexes and so on and so forth. These are the things, these are the tools that we can use in order to ensure this, and we're going to talk about it in this lecture. But this, again, as I said, this is all about the software developer to do this. What is not about the hardware developer is the reordering problem. That if I don't know whether A and B are going to be always maintaining the same order or not, then regardless of like whether or not I have all those kind of barriers and software tools, I might still run into issues. And this is the problem that the hardware has to fix, because this is not something that the software can anticipate or know about. This is something that the hardware has to fix. So this is kind of similar to the out of order problem or the pipelining problem kind of thing. So we have to first fix this problem, then go to the second problem. Okay? Questions so far? How many of you have wrote any parallel program or code, like a pthread or MPI? Have you had racing conditions? Of course. What did you do to fix it? Locks? Yeah. You didn't fix it. Yeah. Fences? Mutex? Yeah, so there are these functional APIs that you can use from the operating system to fix this. Yes. All right, so we're gonna actually talk about those. So if you have no idea about like parallel programming, don't worry. I'm not gonna go through the details of writing a program, but we're gonna give you these different uh, kind of primitives, tools to use. Before that, let's talk about this reordering problem, because that's something that we need to fix in hardware, okay? So how do we fix this? We fix this by first knowing what are the possibilities, okay? This is what we usually refer to as the memory model, Okay, so we can say that, for example, this processor, the like ARM processor, has the memory model of weak consistency, or release consistency, or sequential consistency. Uh, so what are those? So memory model is generally defined as the possible orderings of instructions uh, within one core, okay? What can and cannot be reordered is dictated by the memory model. And when we are designing our ISA and when we are designing our microarchitecture, we have to pick a memory model and stick to that, and we have to announce it to the software developer. So there might be multiple memory models, and we're going to discuss a few of them in the next few slides. But what you will see is that essentially memory model is all about what can be reordered. Can I, for example, reorder stores before loads? Can I reorder loads? Can I reorder stores? And so on and so forth. So there's like two different operations. We have load and stores. Different ways of reordering this is what we call a memory model. Okay? The gold standard memory model is what we call sequential consistency. Sequential consistency is basically telling you that you're not allowed to reorder anything. Okay? So essentially, sequential consistency will give you three things. The first is that processors will see their own loads and store in program order. Number two is that processor sees others' programs load and stores in program order. And then essentially all the processors sees everyone, the global order of load and store in the same manner. So everybody sees the same thing. The same thing that they see is the program's order of the program. So essentially, if you see a load first and a store next, it is guaranteed that the load happens first and the store happens next. But again, remember, this is basically that A, B, C, D thing. It's still sequential consistency is not going to tell you whether A, B happens first or C, D happens first. But it will tell you that it's not possible that B happens before A. And when I say A and B, I'm talking about just memory instructions, so like load and store. So like other instructions, I don't care, like add and like multiply and all those things. I don't care. I can reorder them as I wish. But memory instructions are all happens in order of the program. You had a question? Or did I answer your question? Okay. All right. So sequential consistency, or sometimes chosen SC, is the best possible thing that a programmer can see, right? Because it basically tells you, don't worry about reordering at all. Just focus on the race conditions in your program. Nothing else will happen in your program. Okay? Essentially, what SC gives you is that it makes a multi-core program indistinguishable from a multi-program in-order. So you can assume that this is an in-order processor, that loads and stores happens in order. Then go and figure out the race conditions in your program with us. Okay? What is the kind of negative things about sequential consistency is that it's going to be very slow. So kind of like, through throwing many of the optimizations that we introduce in out of order processing out of into the trash. Because there are many scenarios where you want to issue the stores before loads, or issue loads before loads, or issue stores before stores. Again, remember that this is different than raw data hazard because we're talking about independent, different addresses, not the same address. Still, you maintain the orders of the same address, but independent addresses, for example, if there are two reads from two different addresses, why don't I want to issue these loads in the out of order fashion, right? It might, because if one finishes, I can just issue that load and read it from the memory. Why do I wait for the other independent address to happen, right? So there are these tricks that many of the modern processors use. There was also, like, if you remember, we told you that there is a speculation and speculative loads that you make a guess and you issue it and then you later fix it. Sequential consistency basically doesn't allow that, right? So because essentially if you issue a load, others will see that load, and that will cause lots of problems. So sequential consistency is great, but typically it's not really being implemented in real systems because it's very, very slow. But unfortunately, that means that now we are allowing some reordering to happen. Um, so what are the reordering possible? So you can think about like write after reads, read after reads, read after writes, and write after writes, right? So these are the four possibilities. And again, when I say write after read, this is one address, this is a different address, okay? So this is different than raw data hazard or write after write data hazard and so on and so forth, okay? So for example, if I say my memory model maintains write after read, it means that read after writes, it means that writes must complete before subsequent reads, okay? So if I maintain the order of write, read, it means that write should be completed first, and then I can issue a read. Same story for read reads and read writes and write writes, okay? So this is kind of like a different possibilities. So now the question is, okay, why do you want different memory models, and why there's other memory models in the system? Because of course you can think about many scenarios for optimization. So I've showed you a few of them here. For example, many lines are not even shared, so I don't even need to be worried about their consistency issues. So why am I penalizing my program for lines that are not even shared? So let's actually do them out of order. Uh, some stores don't need to wait because two different stores to do two different addresses. Why do I wait for one to finish and then issue the second one? Uh, and then we already have the ability to do so, right? Like we have the load store queues, and like, you know, we have the retire and reservation station, all of that. So we discuss all those things that we can like speculate and predict and all those things. Why don't we use that? Because that gives us a significant performance boost, right? So this is kind of the counter arguments to maintaining a very strong consistency model, which is a sequential consistency, okay? So as a result, almost all the modern systems using what we call a relaxed or a weak model. So sequential consistency, which you're not allowed to reorder anything, is considered a strong model. Anything that's kind of eliminate one or multiple of these orders of read and writes is what we call a weak model, okay, or a relaxed model, okay? So for example, we can say that not all the loads or stores needs to be in order, okay? And the most extreme version is that we can allow anything to be reordered, but that's usually not the best idea either, because that creates lots of complexity for the programmer that is actually negatively impact the efficiency. So we typically want to maintain some orders, but that order is not needs to be as strict as sequential consistency, okay? Um, so as I said, sequential consistency maintains all four. Weak or relaxed consistency allows a few of them to not happen, or sometimes don't happen, okay? So one very famous one and widely used one is what we call total store order model, TSO model. So kind of like the graphic shows here is that you expect as a programmer to see a sequential consistency. What you really get in most cases is TSO model. So what is a TSO? The TSO, which is actually all the x86, most of the x86 models machines use, all the Intel processors, is that it allows you to kind of reorder a bunch of things, okay? So basically, what you can do is that you can move your own reads in front of your own writes, okay? So you can read faster, okay? That's the thing about TSO. But what TSO provides is that it maintains the order of stores, okay? That's why it's called total store ordering. So it maintains the writes, the order of writes, so everybody sees the same order of write, but it allows you to move the reads in your own core before the writes, okay? How do we do that? If you remember LSQs, the LSQs were exactly that, right? So we told you that essentially when we have a load, we first go through the load store queue. If we see a hit, we're going to actually forward that back. So this will allow us to reorder things and issue things to the memory this way if you want to. Okay? Or for example, if this is not there, then we can issue the load to the main memory. So we can allow this to happen without future stores to happen. So in order to kind of like, because loads is usually the most time-sensitive thing, right? Because you're waiting for the data from the memory to come versus store, you can just write it to the buffer and move on. Loads, you're waiting for the value. So you need to somehow being able to issue the loads as fast as possible, okay? So this what is TSO will give you, that it allows you to issue loads before stores. And that could be an issue in many cases, okay? And then, of course, this will create new problems, such as if you are issuing reads before writes, what happens if the other cores also try to read? The other cores will not see the same value that the initial core sees. So as long as, so remember that unless the store is kind of announced to everyone, the other cores will not see this store. So the TSO will cause this additional complexity to the program where some writes might not be observable by the others, some other writes might be observable. So just keep that in mind, okay? So let me give you an example so that you see that how TSO helps, and then I'm going to give you another example to see that TSO may not help. So in this case, we have two threads, two different cores or two different parts of a program. On the left side, we have a store. I'm just using like a pseudocode, it's not like any ISA or anything. So we have A equal to 1. So essentially, we are storing 1 to the address A. We're also storing 1 to the address flag, okay? On thread 2, we are checking the flag. And if the flag is equal to 0, then we are looping. Okay, so we're kind of busy waiting. If the flag becomes 1, then we go outside this loop and then we're going to load A. Okay? Now the question is, what value we're going to load in A? Do we load 0? Or do we always load 1? And let's assume that initially A and flag are equal to 0. What do you guys think? Let's say if it didn't have TSO, we have all the possible reordering versus when we have TSO. What do you think will happen? Yeah. Yeah, so what happens is that if I can guarantee that this two happens in order, it means that when flag is equal to 1, it is guaranteed that A is already equal to 1. Okay? That's the guarantee that TSO gives you, that stores are in order, which means that if in this thread I see flag is equal to 1, it means that A is equal to 1 is already finished. Okay? So what will happen here is that although, for example, the ordering of these two guys might be different. For example, the second part might run first. At the beginning, since the flag is not equal to 1, it's going to just busy wait. At some point, flag has become equal to 1, which means that we're going to get rid of this loop and we're going to move on to the next instruction. At that point, because of the TSO, it's already guaranteed that A is equal to 1. So what this load will give you is always 1. Okay? It's always 1. If I didn't have TSO, which means that I could issue loads in any order that I want, then this load could have been either 0 or could be 1. Because there is no guarantee that this finishes before this. This order may not be maintained. If this order is maintained, then the code on the right side is also maintained. Okay? And again, remember that the timing between thread 1 and thread 2 could be any sort of ordering. The way that I wrote this program enforced this ordering. So this is when I say that you as a programmer are responsible, that's an example here. That I'm kind of using this busy looping as a way to ensure that this does not happen before flag becomes 1, and then on the other side, I make the flag equal to 1 to make sure that this happens. Make sense? Any questions here? Great. But also TSO does not solve all the problems. So for example, again here, if I can issue loads before stores, or the other way around, you will see that, for example, here I still can read 0, 0 for x1 and x2 because TSO doesn't give you the orderings within the instructions between load and stored. Okay? If I had like another store here, TSO will guarantee that this happens before this one, but TSO doesn't guarantee that these two cannot be reordered. Okay, so keep that in mind. Sequential consistency, though, it guarantees that you never read 0, 0. Okay? So we'll guarantee that this happens before this, and this happens before this. Again, they can be overlapped, and they can be interleaved, but it always guarantees that if I see this, this is already done. If I see this, this is already done. So you can actually come up with different examples. So generally, these kind of consistency questions and problems are a little bit complicated because you need to kind of consider multiple cases. But just keep in mind that the way that you should do is that first, for each core, you have to see what is possible, what reordering is possible, and what reordering is not possible. Then you have to maintain the orderings of cores. So you have to start by like starting one versus the other, and then kind of gradually kind of slide this through the other one to see where these two are interleaved, because all the interleaving is possible, right? So in this case, you can have the first two and then these two, and then start sliding this down. So for example, you can have then this one, this one, this one, and then another one that you can have is this one, this one, this one, this one. So something like that you can have under sequential consistency. Under no consistency, then these two can also be switched. These two can also be switched. So there are many, many possibilities that you can have in this code. Okay? Questions? Great. So summary of TSO, essentially the idea in TSO is that we should be able to reorder our reads before writes. That gives us a significant performance boost. It will help in some cases for the stores, but it may not help in other cases because the load stores might be also reordered. Okay? There are other consistency models. Essentially, on all of them, there's different assumptions of what can be visible at which time, what orders can be done. The main trade-offs is performance versus complexity, and here the complexity is the complexity of understanding the model for the programmer's perspective. And keep in mind that different architectures are using different memory models. For example, as I said, x86 typically use TSO, but ARM and RISC-V is using different models. Actually, RISC-V is using what we call RVWMO, which stands for RISC-V weak memory ordering. Okay? So this is typically what we follow in almost all the RISC-V processors, that they follow WMO or weak memory ordering. What does that mean? So essentially, in RISC-V memory model, we are firing or issuing loads before stores. Okay, so as soon as they hit the load store queues, we issue them to the memory. Okay, what will happen is that we search through the LSUs. So once the memory comes, we issue it right away. We then search LSU. If it's there, then we forward it to this processor, and then the request can be killed, okay, because the value is already in the store queue. If the value is not in the store queue, I mean, the tag is there, but the value is not there, then we're going to put it into sleep, waiting for the store value to come. If the value is not there at all, then we issue it to the memory and then move on. Okay, so it's kind of three possibilities. So the memory request comes to the load store queue. We don't wait at all. We just right away issue it to the memory. We search the load store queue. Either it's there, we forward it, we kill the request. It's there, but its value is not there. It means that the value is getting updated by some other cores or some memory. We put the memory into sleep when we wake it up again when the value comes. Or the value is not there at all, and then that's where we don't kill the request we already requested from the memory, and we move on. All for performance reasons. Okay, this is what we call why it's a kind of weak memory ordering. Okay, so kind of like if you want to summarize it, it's kind of like this: that the reads after writes ordering is relaxed. So I can issue reads before writes. Okay. In other words, newer loads may execute before older stores. Reads constraints is maintained, and then threads can read its own writes early as well, so you can actually order the writes as well inside a thread. And again, if you want, there's actually very lengthy documents about weak memory ordering in RISC-V, but just keep in mind that this is the one way of doing this, and that's what we do in RISC-V. So quite similar to TSO, there are like tiny differences, but just keep that in mind. Okay. Any questions about memory models? All right, so let's talk about the second part of the memory consistency problem. And remember, I told you that we first need to know the possible ordering. Then we need to write a program that is race-free. Okay? So how do we know the possible ordering? We need to check the memory model of the processor that we're going to write. So keep in mind that these parallel programs that you write typically are not directly transferable from one architecture to another architecture. So if you write something for RISC-V, it may not work for x86. Or if you write it for sequential consistency, it may not work for TSO or weak memory model. Okay? So this is like, it's one thing to keep in mind. But generally, in order to start writing a program, the first thing that you need to know is the memory model. Once you know the memory model, you know the possible orderings, then you can start writing your program. Okay? So there are two solutions. The first solution is I don't add any other guards or helps. What I do instead is I write a program that any order will always result in the same result. Okay? This is what we call a race-free program. It's usually very, very hard to write, but you technically can write a program that doesn't have any race condition, which means that I don't care which order you run this, it will always result into the same value at the end. Okay? This is okay, but it's usually not the easiest way. That's why we need to add some more capabilities. One option is that we can keep track of different things in hardware. If we see violation, we can fix them. This is usually very costly because we need to track various violations. Instead, what we do is we are using different synchronization primitives. Okay? So the idea of the synchronization is that we use either software or hardware or a combination of both in order to make sure that the timing between the cores are something that we know exactly what that is. So we maintain the timing between the cores. We synchronize them using different primitives. What are those primitives? The first one is like there are two general solutions. The first one is what we call a producer-consumer model, which we always guarantee that data is produced by one and consumed by the other. And we always maintain the order, so we never let the producer happens after the consumer. The second solution is what we call mutual exclusiveness, which means that we always guarantee that the shared resource, whether it's a memory line or various different things, always can only and only access by one of the cores. There is no line that can be at the same time written by two. This is what we usually refer to as mutexes or locks that you probably know what they are. Okay? So let's talk about them. Let's talk about this first one. How do we maintain this kind of order? We maintain the order using what we call a fence. Okay? So the fence is basically an instruction, actually. It's within the ISA. What it does is that it enforces all the memory operations before the fence to happen, make sure that all the memory instructions above the fence happens before the fence is reached. Okay? So for example, if I have like if I have a bunch of stores and loads and so on and so forth, actually, let me write it this way. Store, load, maybe another load, and store. So these are same address, different address, whatever. Then I'm going to have a fence. And again, fence is literally an instruction. Then I'm going to have another, let's say, sequence of load, stores, whatever. Okay? So what this does is that this will follow whatever memory order that you have, whether you can reorder them, you cannot reorder them, I don't know. But what this fence guarantees that at this point, all of these guys has to be finished before I can issue any of these guys. So again, before and after a fence, I can reorder as much as I like based on the memory model. But once I reach to the fence, I ensure that everything above it already done. Nothing below it has happened. Okay? This is what we call a fence. This is very, very useful instruction because it's kind of maintain this producer-consumer. So you can think about everything above the fence is the producer, everything below the fence is the consumer. So if I can maintain this type of programming, then I can have and make sure that my system works correctly. In RISC-V, we typically have 4 options. Okay, so you don't need to do all the memory operations. So you can think about memory operations as 4 different things: inputs, I/O inputs, I/O outputs, memory reads, memory writes. Okay, so you have 4 different options. You can have any order of these. Okay, so you can have, for example, what we call a fence RR, which means that all the reads should finish before the future reads. It doesn't say anything about the writes or the I/O. It just maintains the reads. You can have, for example, fence RW. This means that all the reads and writes, all the loads and stores should be finished so that I can issue new load and stores. You can have RWIO. This means that not only writes, read, and writes to the memory, but also reads and writes to the I/O is also happening. Main thing that you need to know is mainly RW. Don't worry about the inputs just yet because we haven't talked much about I/Os. The way that we actually write this is, as I said, this is literally an instruction. So you have the opcode and RD and all that. These flags are basically here. So for example, if I write 1 to bit 27 and 26, that's how I kind of maintain this RW, this is called predecessor and this is called successor. So I change the predecessor and successor based on that. Okay? So this is the way that we implement this in RISC-V. Okay? So now that we know that within the core I can maintain this, now the question is what happens between the cores? Between the cores you can also have some form of a fence. Typically we call this a barrier or a semaphore. This is kind of something that mainly implemented in software at the operating system level. The idea of a synchronizer or a barrier is that not only you want to kind of do all the reordering within a core, you also want to, for example, make sure that I want to have a sequence where I want to make sure that this runs first and then this runs. So what I do is that I create this barrier here, okay? And what this barrier does, it basically says that I only move forward until both of these programs reach to their respective barriers. Okay? What this means is that I cannot run this program until this core reaches to the barrier, which means that at this point it's guaranteed that these two guys are finished. So this way I can maintain the order as I wish. I can move the barriers whichever I want, and this will always make sure that if you want to run those first two codes for core number 1 first, and then the other guys second, you put the barrier between the two and those two cores, and this will make sure that this will work this way. Okay? So it's different than the fence that you kind of serialize the loads. This is kind of a synchronization between the cores. We call them semaphores or barriers. Usually we call them barriers. It's easier to do that. You can implement barriers both in software and hardware. For those of you taking operating system, you've probably seen, I don't know, have you seen an implementation of software barriers? Is it discussed in 111? Yes, kind of, okay. You can also implement this in hardware. This is also common. In hardware, the idea is very simple. Think about every core having a flag, a one hot, coding. So let's say if I have 4 cores, I will have 4 flags next to each other. When I reach to that particular port, I'm going to switch the flag to 1. So I'm going to set my flag when I reach to that point. Once all of these becomes 1, then the OR of them are 1, and then I can move forward. So essentially, everybody waits until the outcome of the OR becomes 1. This is an OR, right? So so all of them, once all of them becomes 1, then this will move forward, right? And this will again guarantees that when all of them reach the barrier, then they can move forward. So think about this: is that we stall a processor once it reaches to that point. Once the outcome becomes 1, then you uninstall the processor and let it continue. Okay, this is how you would implement this in hardware. All right. So this is kind of like the producer-consumer. Yeah. It can be. So it's called hardware OR. So the hardware OR is essentially when all of the flags becomes 1, the value becomes 1. So this is what you usually call it. Yeah. So think about this, that like these are all wires, and then when all the wires becomes 1, then the final value become 1. So this is usually the definition. Yeah, and yeah, equivalent logically is an and. Okay. So this was the kind of producer-consumer kind of behavior, but we use fences and barriers to ensure the orderings. But what about mutual exclusiveness? That I told you that this is the second option that you can have in order to achieve. So essentially, mutual exclusiveness gives you this property that only one process can access a shared region at any given time. Okay? So what you would do is you put these two things. So think about this as a function. Okay? So you call it acquire lock and release lock. And you have it here and here as well. Okay? So what will happen is that you put both of these two instructions into this mutex, this lock region. What will happen is that basically this says that only one of these cores at any given time have the lock. Either this one has the lock or this one has the lock. I don't know which one. I cannot guarantee that core 1 gonna get the lock first and core number 2 gonna get the lock second. But I know for a fact that if this is running, this will not be running. Okay? So basically what this say is that I'm gonna either see A, B, C, D, or I'm going to see C, D, A, B. I cannot see anything else. I cannot see the overlap. I cannot see this one is running, then this one is running, then this one is running, and this one is running. This is not possible. The lock is acquired, or run the whole thing in the lock, and then move on to the next one. Another question is, can I reorder things within the lock? The answer to that, it depends on the memory model. Some memory model allows you to reorder things within the lock. Some memory models doesn't allow you to reorder things within the lock. Okay? Yeah. The question is, can you put locks on the memory? So locks is actually an API. So it's a primitive, a software primitive. So you put it into your programs. Yeah, it's provided usually by the operating system. Yeah. So the question is, if you have TSO, can I reorder a store and loads? And yes, you can. Mhm. So you can have like BA, DC, or CD, or whatever. Mhm. But again, it eliminates some possibilities, right? In the past, you could also have like BA, BDAC kind of thing, but this one doesn't allow you that. So it eliminates some, doesn't eliminate the others. Typically, what we do with locks is actually what we call release consistency. So the release consistency is that we guarantee that when we release the lock, not only we release the lock, but we make all the reads and writes at that point visible to everyone. So by the time that we release the lock, everybody will see our loads and stores, okay? And again, you can assume that whether or not you can reorder things within the lock is a separate story, but release consistency basically says that reorders, the orders, like all the reads and writes at that point is visible to everybody else, okay? Uh, Other than this, any other reordering is possible, okay? So keep in mind that the release consistency is another memory model, basically, okay? So it's a weak memory model, but it's particularly the name release consistency is because when you release the lock, you will see the ordering, okay? So how do we actually implement this acquire and release? In software, it would look something like this, that let's say acquire lock is a function that takes locks as an input. Think about lock as like a value that's either 0 or 1. And then we kind of busy wait, right? So acquiring is kind of a busy waiting that if lock is not equal to 0, sorry, it's not equal to 1, I'm going to wait. Sorry, if it's not equal to 0, I'm going to wait until on this value. Once the lock becomes 1, I acquire the lock, which means that I write 1 to it. When it's 1, it means that it's busy, it's not available. And then I exit this program. So at this point, I know that I'm the one that acquired the lock, and I make the lock busy. And so the others cannot acquire it, okay? If you want to see the assembly version, would look like something like this, that let's say x1 is the address of the lock. So you keep loading your address of the lock to the, to some register, let's say RA. And then you do branch not equal 0, and then you loop back. So this is your while loop. This is your busy loop. If at this point it's the RA is now equal to 0, then you write 1 to it. So you add RA x0 and 1. You store it to the lock address, and then at this point you can return, right? So you can return at this point from the program, right? So this is like a binary, sorry, assembly equivalent of that in RISC-V. Any questions here? One last thing before I let you guys go. This has, and then release, of course, is just the simple thing to release is just lock equal to 0, which means that you store SW or store to the address of the lock, which in this case is store RA, store, like you do add-I, you have to do add-I RA x0 and 0, and then you store RA 0, 0, and x1, right? So that's what you do in the release, right? So you just write 1, okay, write 0. So what is a big problem with this? Consider 2 cores like this. that they're both trying to acquire the lock, okay? If I'm trying to acquire the lock, and if I have this overlapping, consider a scenario like this, that I run this. Before writing this, I run this. So both of the cores thinks that they have acquired the lock, right? So if this source happens after this load here, actually, then both of these cores thinks that they read lock is equal to 0. Lock is available, right? So overlapping between these two sequence of instructions is actually terrible. It actually makes this lock to not to work. So how do we do that? We need to run this lock and release such that we make sure that they are not overlapping with others. If they overlap with others, then basically it's not going to work, because there might be scenarios that both of these programs thinks that they have the lock. How do we do that? We use this thing called atomic instructions, okay? So this is another hardware primitives that we're going to use. The idea of atomic operations is that we guarantee that that instruction is not interrupted, executed in order and uninterrupted, which means that other cores cannot run the same instructions. How do we do that? We're going to explain it next time. But just keep in mind that in order to implement such a thing, we need to have atomic operations, which means that if one is running, the others should not be able to run the same thing. If they do, they will both at the same time, because of the orderings, they might think that they have the same thing. That breaks the assumption that this is a mutually exclusive code. Okay? All right, so happy Thanksgiving, guys. No class on Thursday. I'll see you guys next Tuesday.